Hello guys, nice to see you after this long weekend. Hope you relaxed, full of energy for your further studies. So let us start from recall of important information which we discussed last time. So we introduced three laws of motion, and let us start with refreshing our statements which we made um, for all of them. So who can define first law of motion as we discussed it? Something was about inertial system of coordinates, so inertial system of reference, free for quasi-free body, moves how? Can it move with acceleration?
With no extra forces X on the object, or all of them are
Compensated.
Because the real force, the real force will be equal to zero.
Yeah, so that definition of free and quasi-free body. So all free, we don't have any forces exerted on the body, which is quite unique situation that is difficult to realize. But most realistic cases are associated with quasi-free bodies, and those are bodies when we have external forces exerted on the body, but vector sum of all forces is equal to zero, so the net force is equal to zero. So when we have an inertial system of reference, such the case, a body like free or quasi-free body, can it move with acceleration? No, because the net force is equal to zero. So it cannot move with acceleration. So it means that magnitude of velocity vector doesn't change. What about orientation? Can orientation of velocity vector change? Doesn't change. And that is because acceleration is equal to zero. If we have the case when direction of velocity vector is changing, we deal with centripetal acceleration. That already violates our definition of the system. So means both magnitude and direction remain constant, means that object can move only with constant velocity along a straight line without change magnitude and orientation. Or another option, it can be just reside in peace with no motion at all. So that's definition of the first law of motion. So we can define it just as a recall here. First law of motion, sum of all forces exerted on the body is equal to zero. And in that case, velocity vector is constant or it's equal to zero. Okay, so what about second law of motion? That gives us a relationship between acceleration, force, and mass of the body. So we can represent it in different forms. It can be either quite common force equal m times a vector. But keep in mind, to be specific, this is also the net force. So means the vector sum of all exerted forces on the body. So we just don't write this sign of sum, but you need to understand that this is resultant force. Or we can consider acceleration as a reason of exerted force on the body. So we can write acceleration vector is force vector divided by mass. So we also determined what is this inertial mass, what's the difference with gravitational mass, how we can measure acceleration and inertial mass. And there is one more law of motion, the third one, which tells us about what? Action and reaction. So if there is some force exerted from body 1 on body 2, let us denote it here. Some body 1 body 2, and this is force so-called 1, 2, exerted from body 1 on body 2, there always will be force 2, 1, the reaction force from the second body on first body, with the same magnitude but different orientation. So these are the three laws of motion, and we today continue to discuss some different applications of laws of motion in order to see how it can be applied in some like different scenarios. So today let us continue, because we started this discussion a little bit last time with some inclined plane. Today let us continue further. And the first system which we are going to discuss will be some elevator with a block M in this elevator. And let us consider axis X, which goes vertically upwards as positive direction. So at stationary conditions, when there is no motion or constant velocity of motion of this elevator, what do we have? We have weight of this block exerted on elevator, and also, according to third law of motion, we have a reaction from the side of elevator upwards. So under stationary conditions, or case where we don't have any acceleration of this system, we can write that n, we consider it as positive because direction coincide with positive direction of x, minus mg. In this case, it goes downwards, so in negative direction of axis x, and that will be equal to 0. Since we don't have any acceleration, acceleration is equal to 0. So they compensate each other. So now let us consider one case when acceleration vector is oriented upwards along axis x. So in this case, we can write n minus mg. So it's the same case as previously, but this n will be already different from first case. And that will be equal to m times a, mass of the block times acceleration. And since this acceleration aligned with the axis x, it will be positive. So in this case, we can express n as mg times ma, and that will be equal to mg times a. So we see that the reaction of the elevator will increase in comparison to first case, that was just mg. Now it's mg times a when this acceleration is pointed upwards along axis x. So obviously there is another option, and that will be when acceleration is pointed downwards. So we can write that n minus mg will be equal to minus m times a. And from here, we can write that n new reaction, which will be established under this condition, will be equal to mg minus ma, m times g minus a. So we have the case when reaction of the elevator will be reduced in comparison to stationary condition because of this additional acceleration. So keep in mind, now we consider example of a system of reference which is not inertial, because this elevator is moving with some acceleration in this system of reference with respect of which we consider our mass, then it becomes not inertial system of reference. But we can also go further and consider some special case, which is acceleration equal to acceleration of free fall. So if A is equal to g, then n becomes equal to 0. So that is the case when we have kind of imitation of free falling conditions, because reaction of the elevator of this basement base of the elevator is equal to 0. Nothing acts on the body, and body, this block, will just experience free falling. So now let us go to another example and include motion, like circular motion, which we considered a little bit earlier. We need to consider circular motion now in the scope of three laws of motion in order to see their application in a new type of system. So in this case, let us consider a vertical axis, some rope attached to, like in this point, upwards, and block with mass m attached to the rope. So length of the rope is L. So this system, the rope with the mass, will perform some uniform circular motion with angular frequency omega. So the trajectory this block will draw will look like this. So it's circular trajectory. So let us consider what forces will be exerted on this block. So suggestions? So obviously, let's start from most general. So there will be weight of this block. So we have this weight of the block will be mg. Then mention centripetal. Well, that's centripetal acceleration and force. We remember the difference between centripetal force and centrifugal force. Centripetal acceleration is pointed toward the center of the circle of the circular trajectory, and the same direction is for centripetal force. But we are now external observers for this system, and from the external system of reference, we will kind of see the effect of so-called centrifugal force, which is exerted on this block M, which tries to pull block M further from the center of this circular trajectory. Circular trajectory, by the way, an important parameter. We need to highlight that it has some radius r. So that will be our centrifugal force. It will be m times omega square times r. Omega square times r we discussed last time when we introduced in circular motion, we introduce angular velocity. So centripetal acceleration magnitude is given as omega squared times r. And in order to get force, we multiply it by mass of the block. So we neglect with the mass of the rope. Now, what else? We need one more force. Tension, yeah. And that is because we keep this all together. Otherwise, it would just fly away. So we need tension which compensates in both direction x and y. We will consider it keeps system together. So that will be tension. So now the question will be for us, what will be the angle theta of this deflection of rope from the axis, vertical axis of rotation? How do we approach this? Let us draw these vectors, like these forces which are exerted on the block, separately, so we have it not overcrowded. So this is our block. Here is mg. Here is m times omega square r. And here is tension. So let us draw a system of coordinates will be x and y. So now, if this angle theta is here, then here we will have also angle theta between tension vector and vertical y-axis. So what we can write, we know that this system is in steady state condition. So it moves. We have some certain motion y-axis defined here, but all parameters remain constant. So mass, length, by definition, they are constant. Angular velocity constant means it doesn't change over time, and that implies that this angle theta will be also constant. So at this given set of conditions, we can write equilibrium equations for axis y and x. So what do we have in axis y? We have T tension in the rope times cosine theta. That is equal to mg. So they should compensate each other. Projection of this vector, tension vector, on axis y should compensate weight of the block because there is no motion along axis y. The same we should write also for axis x. So we can write t times sinus theta is equal to m omega squared times r. So with this, we have a system of two equations which can express tension in terms of other parameters in a different way. So that's what we want to do. We express tension from equation 1 and equation 2, and then equate them to each other. So tension from first equation will be m times g divided by cosinus theta. And from the second equation, tension is m times omega squared times r divided by sinus theta. So now what we can do, we have the same left sides, so we can equate these right sides. So it will be m times g divided by cosinus theta equal to m times omega squared times r divided by sinus theta. So what do we have here? We can cancel out m, but there is one parameter r, radius of the circular trajectory, which we still don't know. How do we define this radius? Radius is equal length of the rope times sinus theta, L times sinus theta. So you see from here we have this length of the rope, this angle theta, and this will be the radius of the circle. So now we can substitute R with known parameters. I mean, known, we know L, we know the length is given. So that will be G over cosinus theta equal to omega squared times L sinus theta divided by sinus theta. So now we cancel out sinus theta from numerator and denominator, and eventually we get cosinus theta is equal to G divided by omega squared times L. So this is our equation, which relates angle theta, deflection of this rho from vertical axis of rotation, with three parameters which actually define. So if we increase G, well, let's say G is a constant parameter, since let's consider that we are on planet Earth and acceleration of free fall is constant. But there are two parameters in denominator which can change. So angular velocity and length of the rho. So if we increase length, cosine theta will decrease. And what does it mean about theta? L increases, cosine theta decreases, and theta will increase. Since cosine theta decreases, theta increases. So that's one factor which will define the angle. And there is another more influential factor, since we have angular velocity in second power here. So you always need to pay attention on parameters which are more important for the dependence which you are studying. So in this case, of course, angular velocity is the parameter which defines the features of the system the most. So if we increase angular frequency by a little bit, we see quite a dramatic decrease in cosine theta, and that will result in dramatic increase of angle theta. So it will just deflect further and further, and at some point when omega squared will reach such value that we can neglect with the G in comparison to omega squared times L, cosine theta will approach to 0. And that means that theta will approach to pi over 2, or that stands for 90 degrees. So it is possible to increase angular velocity to that extent that this block will go like up and will reach almost to 90 degrees. So now the question is, any suggestions what could be a limiting factor for this to happen, that it goes to 90 degrees?
Like the force string can hold.
Oh, what? Yeah.
I'm assuming at some point string can just height.
Yeah, you are right. So that is a property of material. You need to think about this because this string, rope, wire, whatever it is, it possesses certain maximum force it can handle. If this centrifugal force, which will increase dramatically with increase of angular velocity, exceeds this capabilities of the rope, it will be damaged. So that will be a limiting factor. Another limiting factor is also this hinge where you fix this system. So even if rope can handle certain force, doesn't mean that hinge will do that. So always when you consider some systems, try to think about limitations, because from mathematical point of view, yes, you see that we can reach 90 degrees. However, objectively, that is quite a challenging task to do. Yeah. Huh? That is a good point. We didn't mention about it, so we consider that's happening in vacuum. There is no friction and no drag force with air, but definitely we will soon, probably next lecture, we will introduce drag force and also keep that um, in our discussion. So now with these examples, I would like to proceed to another one, which is a bit more interesting from point of view of force exerted to the body. So far, all our examples were considering only constant forces. So means they don't change their orientation and magnitude with other parameters, let's say position or time. Force we considered so far is constant, and that is a good example when we deal with weight, for instance. So weight, that is mass times acceleration of free fall, orientation of acceleration, free fall acceleration is constant. Magnitude of this acceleration is also constant if we don't move far away from the surface of the Earth. Mass of the object, if we neglect some options for evaporation or other loss of mass, remains constant within the time of experiment. And that is a perfect example of constant force which is exerted on the body. However, that's not always the case. And sometimes we need to deal with forces which depend on other parameters, so they change. That means that acceleration, which is resulted from these forces, time-dependent force, for instance, on the body also changes with time. And when we want to determine position of an object, taking into account kinematic equation and this time-dependent force, it can become quite a challenging task. So we will just consider some example without detailed solution here. We will do this detailed solution a little bit later when we consider harmonical motion. It will be a bit later, but now I just want to highlight use this example in order to show how laws of motion can be applied in the case of time-dependent forces. So a very good system for this example, which we will consider quite often in the future, is the system spring and block. Without any friction, we just have a block attached to a spring. So let us show it. This is our spring, this is our block. With some known mass m, we neglect with the mass of the string. The properties of the string is defined by some string coefficient k. So now at this point, we consider this system in equilibrium. So that is axis x, and this is coordinate y. So let us assume that this system is pushed out from equilibrium condition, and this block is moved towards the positive direction of axis x to new position, like coordinate x equal to a. Capital A stands for amplitude value, and this is mass m. So means magnitude value that we push the system out of equilibrium. It reaches coordinate x, which is maximum displacement from original equilibrium condition, and that results in the case when we don't have any motion of this block anymore. So it was moving towards right direction, reached maximum point, it stopped at the maximum point, and at t equals 0, it's still standing at this maximum point. So it doesn't move neither to the right nor to the left. So we can write here some boundary conditions which we need. And that is at t equals 0, that's for our consideration, what we consider. X coordinate of this block will be A. And also we can claim that at t equals 0, since the block is located at the maximum displacement from equilibrium condition, that velocity, which is first derivative of position over time, is also equal to 0 at t equals 0. So these are so-called boundary conditions, just conditions which describe a specific system in given moment of time, which we arbitrarily can pick up as t equals 0. So now, since this system is out from the equilibrium condition, there will be some force exerted on this block, and that will be spring force. So spring force is defined as follows. It's equal to minus k times displacement vector. So we can write delta x. So what does it mean? We have some displacement from equilibrium condition to maximum displacement amplitude value, and this force will be proportional to the displacement. So spring force is proportional to displacement. With this coefficient, proportionality coefficient k, which is spring's coefficient and defines the properties of the spring, how stiff this spring is and how much force it exerts on bodies when it goes to some extension or contraction. And also keep in mind this minus. So minus is important here because spring force is always oriented in opposite direction to the displacement vector. So if we move this block towards positive direction of axis x, displacement vector is in this direction, and spring force always pointed in opposite direction to the displacement vector. So now let us involve here acceleration vector. So obviously, according to second law of motion, we have some force, which in this case spring force, exerted on the block. We don't have any friction. So if there is block with mass m and there is some force exerted on this block, it will start to move with acceleration. So we can write now that according to third law of motion, that minus k times delta x, its displacement, will be equal to let's put here m first, m times acceleration vector. So of course we are dealing with one-dimensional case along axis x, so we don't specify the same x, because forces along axis y, they just compensated, and we can neglect with them. So we don't consider anything along axis y, only one-dimensional case. So this is example of second law of motion in this particular case with the string. And from here we can express A. And if we stick to one-dimensional case, we can neglect with this vectors also. M will be equal to minus A acceleration is equal to minus k divided by m times delta x. So we have expression for acceleration. And what is special about this case? Any suggestions? it's not a constant acceleration. So this acceleration is a function of displacement, means in this case actually of coordinate position of block with respect to axis x. So if it depends on some parameter, it will change as block moves, because at moment t equals to 0, this block is at coordinate x equals a. So that will correspond to certain spring force exerted on the block. Then, as t time goes further, this block, under effect of this spring force, will move in opposite direction to axis x, and its position with respect to axis x will change. So it will move towards the equilibrium condition. That means that position is a function of time, and acceleration itself also is a function of time. So we can write that acceleration as a function of time is equal to minus k divided by m times x, coordinate like position as a function of time. So if force and acceleration is a function of time, then we need to take this into account when we want to determine position of this block at any moment of time. So this is one of the first examples when we consider force as not constant, but time dependent. And in every time when we deal with some time dependence of parameters and want to know this function, original function as a function of time, we will end up with so-called differential equations. So let us see how we get a differential equation for this particular case. What do we have here in the left side? It's acceleration. What is, by definition, acceleration? Change of velocity with time, so that we can write acceleration is first derivative of velocity over time. And what is definition of velocity? Position over time. Yes, so that means that acceleration is the second derivative of position over time. So we can write d squared x over dt squared. So that is for the left side. We can write here d squared x over dt squared is equal to minus k over m x. I don't put here time dependence, that's already clear that it's x is a time dependent function. And let us rearrange it, so we will get d square x over dt square plus k over m times x, and that is equal to 0. So this is so-called second order linear differential equation. You will solve many of these during calculus a little bit later. So now we don't go step by step in the solution of this differential equations, since this we will do this a bit later when we consider harmonical oscillation, harmonical motion. But now it's just a clear example what happens in terms of application of second law of motion when we deal with time-dependent forces. So now we have here information about this function x. So we have first derivative, so second derivative of function x times this unknown function plus unknown function x multiplied by some coefficient k divided by m, and that coefficient is defined by properties of the spring and mass of the block attached to this spring. When we solve this differential equation, obviously we will need our where they are our boundary conditions. So here they are, because every differential equation, when you deal with some real physical system, we cannot end up our solution with some random constants which are not defined. We need to define constants. Constants we define with boundary conditions which describe the system at given moment of time for this case. And the solution of this differential equation involving this boundary conditions which we define for t equals 0, position is x equal a, and velocity is equal to 0. We have x as a function of time equal to a. This is amplitude, maximum displacement of the mass from the equilibrium condition. And here will be cosinus square root k over m times t. So that will show us position as a function of law when we have exerted time-dependent force defined by the spring. So we have spring force, which is time-dependent, position-dependent. Eventually, taking this into account, we end up with such differential equation where this stands just for acceleration, its definition of acceleration, second derivative of position. Here is our force, spring force. In the scope, we consider this in the scope of second law of motion, assuming that we don't have constant force because that would be very trivial, but force as a function of time in this case, or position along axis x. And this is the solution, assuming that we stick to our boundary conditions defined at the beginning. So with this, I think that is enough for today. We will continue our discussion of laws of motion application next lecture also on Friday. So we will introduce friction force, drag force, and we'll consider certain examples of applications laws of motion already involving friction and drag force.